Hi folks, this is Maria, and in this video I'm going to talk about empirical and molecular formulas. So in order to do that, I'm going to talk about the difference between empirical and molecular formulas, why you might actually want to use these as a chemist, and then we're going to have to talk about percent composition by mass in order to discuss this. And I'm just going to go ahead and review a few different types of problems you might end up encountering in class. Okay, so what's the difference between empirical and molecular formulas? Molecular formulas just tell me exactly how many atoms are found in a molecule or compound, whereas an empirical formula, just the simplest whole number ratio of atoms in a molecule or compound. So let's do some quick practice just so you get that idea in your head about what's the real difference between an empirical and molecular formula. So if I start with this molecular formula here, C2H6O2, the empirical formula would be CH3O. Easy enough. I just have to essentially divide each of these by 2. That gets me a simplest whole number ratio. Awesome. Let's do another practice. N2H4. Okay, so the empirical formula for that one, again, easy enough. Divide both by 2. NH2. Now sometimes you might end up with one where it's a little more complex. If it's something like this, it makes your life a lot easier to kind of group those atoms together by what type of atom they are. So in this particular case, if I group these atoms together, you'll notice pretty quickly the empirical formula, I can't simplify it anymore. And that's okay. Sometimes the molecular formula and the empirical formula, they're the same. Just something that happens. That's all right. Okay, so students always ask me at this point, well, why do we actually care about empirical formulas? Well, there's 2 different reasons. Sometimes it's helpful for categorizing different chemical compounds. So there's a lot of sugars, for example, that we'll talk about in biology next year, where they have, in fact, the same exact empirical formula. Don't worry, you'll learn more about that next year. And then it's also really helpful for figuring out new compound formulas. So if I'm making a new compound, if I use elemental analysis, where it tells me how much of each element I have in my final product, it's really helpful to figure out some formulas that I have. Okay, so the very first thing we have to do is actually fairly easy, percent composition by mass. So if I give you a formula, what would the percent composition by mass be? Easy enough. We're going to do NO2. I just have to come up with the molar mass of NO2, which you've been doing for a while at this point. Awesome. I end up calculating 46.01 grams per mole. And then you just have to do percentages out of the molar mass. So there's 1 nitrogen. That 1 nitrogen would be 14.01. So I divide it by my molar mass of NO2 times 100. And with sig figs, I end up getting 30.45% nitrogen. Really important, please label which element you are looking at. If you just leave it like this, it's really hard for your teacher to tell exactly what element you are talking about. So just important to keep in mind, label things well. Then if I have oxygen, do the same sort of thing, do my sig figs. And if you're wondering where I got the numbers on top, just remember it comes from the compound itself, how many I have of each. I only have 1 nitrogen, so that's why I have 1 nitrogen on top of this one. But in this case, there's 2 oxygens, so that's where I got the 32.00 grams per mole oxygen, because each oxygen would be 16. 16 times 2, 32. Cool. So that's percent composition. Not too bad, right? We're going to start with what I would say is the least amount of work you might ever have to do for if you were given a problem like this. So if you were given molar mass and the empirical formula, you might be asked to determine the molecular formula. So this is also something that could be tacked on after you've figured out the empirical formula. Just something to know. Okay, so if the empirical formula of cyclononane is CH2 and the molar mass of cyclononane is 126.24 grams per mole, come up with the molecular formula. All right. First thing you do, you got to come up with the molar mass of the empirical formula. So that's the CH2, right? When I do that, I end up getting 14.03 grams per mole. All right. My next step is just divide the given molar mass, the molar mass of my compound, by the molar mass of the empirical formula. So the given molar mass in this one was 126.24 grams per mole. And then what I calculated in this first step was the molar mass of the empirical formula. So that's where I got those numbers. And then I get about 8.997, and then there's a few more numbers after that. That rounds, though, to 9. It's pretty darn close. Hopefully you'll agree with me on that one. Pretty darn close to 9. So since it rounds to 9, all I have to do then is take the empirical formula, which remember, CH2, and by the number that I determined in this last step, so 9. So all I have to do is go, okay, well, I have one C. Okay, so my formula should be C9, and then I have two H's in my empirical formula. So 2 times 9. So it should be C9H18. And funny enough, that is in fact the answer for the molecular formula for this one. Cool. So that one's a shorter one. Now I'm going to go through two longer problems. Okay, so what if I asked you to determine the empirical formula from percent composition by mass? So you don't have to determine the percent composition, you already have it, but come up with the empirical formula. Okay, sounds good, we can do that. So in this one, we have 85.6% carbon by mass, and then 14.4% hydrogen by mass. So the first thing you want to do is essentially kind of convert that percentage to actual mass. Now, how do you do that? It's actually fairly easy. You just go ahead and you assume you have 100 grams of an unknown compound. Well, if that's true in my unknown compound, if I have 100 grams, I know 85.6% of that would be carbon, and I know 14.4% of that would be hydrogen. So therefore, that's pretty much my masses. Now, students frequently ask about why 100. Completely fair. The only reason why we choose that is just to make the math easier. You could pick different values. It just makes your math a little bit more tricky. I would stick to 100 grams just because it makes your math a lot easier. All right. So then all I have to do is take these masses and then convert into number of moles. Use my periodic table, do a little dimensional analysis. No problem. Okay, so now that I've calculated the number of moles of each of my compound, my next step that I'm going to end up doing is divide by the smaller number. Now you can definitely agree with me that that's the moles of carbon in this particular case. So if I'm going to divide each of these by the smaller number. Okay, well, a number divided by itself, 1. And then if I divide the 14.2574 by 7.1273, it's about 2. Okay, so if that's true, that's really just telling me, well, I know that this divided by this, because this was carbon, important to keep in track of that when you're going through. Since this was carbon, that means that there's 1 carbon for every 2 hydrogens. And so that's where I get my empirical formula of CH2. Awesome. All right. There is one thing to know, and that's if these two numbers right here, if they weren't whole numbers, if they weren't really close to whole numbers, you have to multiply them until they are a whole number before you actually apply them to an empirical formula. So make sure you keep that in mind. I'm going to show you an example in the next problem, but just keep that in mind. All right, so here's another potential type of problem that you could end up with. So determine the empirical formula from mass data. So if I have a compound and the weight of that compound is 21.06 grams, and I know 18.57 grams of that is carbon, and the rest of the sample is hydrogen. All right, great. So I just have to do some simple math first. I already know how much of this is carbon, but how much of it is hydrogen? Easy, I just do some quick math. And so I have this many grams of hydrogen and this many grams of carbon because that was already given, so good, yay. All right, you're gonna notice a pattern, of course, convert that mass into moles. So once I do that, that's how many moles of carbon I get, that's how many moles of hydrogen I get. Awesome. And I bet you can kind of figure out from the one before. I just need to find the smaller of the numbers and then divide both of these by the smaller value. Okay, well, number divided by itself should be 1. And this one, when I divide it, I get about 1.6. Now, as I said before, I have to multiply both of these numbers into the whole numbers. And that's important. 1.6, that's a kind of funky number, right? So what number is the smallest number that I can multiply both of these by to get a whole number? Well, in this particular case, maybe just take a moment, kind of think about your fractions, maybe that will help. But if you're thinking about it, multiply both of these times 5, because that will end up giving you a whole number for both of these. So if I do that, I end up getting this would be 5, and then this would be 8. So now I can apply it to my empirical formula. And so that would be my answer for this particular problem. Great. Now, there's a few tips I want to give you. This is one of my favorite rhymes. I hadn't heard it before. Becky and I were talking last year, and I just love it. So, percent to mass, mass to mole, divide by small, multiply to a whole. So it's a good little sing-songy sort of thing, but it reminds you of something that honestly most students forget. And you know what most students forget? They forget to turn whatever your mass is into moles when you're trying to figure out an empirical formula. This is often the step that students forget. I would highly recommend that you get in that mentality that you're going to have to turn something into moles before you can actually start coming up with empirical formulas. It's really, really, really important. A lot of students will do this first step and then skip straight to the third and then the fourth. And it makes your life a whole lot harder. Now, sig figs, let's chat about that real fast. They don't actually really matter when you're determining the empirical formula or molecular formula because you're looking at whole number ratios. Because of that, carry at least 4 places after the decimal point. If you only carry 1 or 2 places after the decimal point, you are going to make your life much harder. You're not going to get a value that's easily recognizable as something that you can either round or multiply by a certain number. Speaking of that, the hardest thing to kind of know is when you should multiply or when not. In this class, you are only. You should kind of recognize that either it's going to be a whole number right away, hooray, or if you end up with any of these values. So if it's 0.25, 0.5, 0.75, so any of these ones, you'll recognize these are all kind of 1/4 things. If I'm looking at any of these, the 1/5 or 1/3 sort of ways are kind of how I think about it when going through. Make sure that if you get one of these numbers, you cannot just round. I can't just be like, oh, 0.2, well, that's pretty close to like a whole number. Not quite yet. So make sure that you multiply when you see a number like that. Just something that you'll pick up with more practice when going through. All right. So there is a question on page 19. You must try it. It's one of the ones in your packet. I know it's a few pages later, but go ahead, try that. It's similar to some of the problems. So if you need to go back and take a look at any of this video, you can always rewatch this video while you're trying to do that problem. Make sure you try it. All right. With that, it's the end of this video. And make sure you ask your teacher any questions when you're going through these problems and if you don't understand anything. All right.